All right, let's continue with some additional statistics for number-to-number relationships as well as visualizations this time. And I want to start by going back to our data here. Let's say we want to understand the relationship between age and charges. You've already learned how to calculate a correlation coefficient between those two, but let's next create a visualization. And for number-to-number relationships, the default or ideal visualization is a scatter plot. So what we need is to grab these two features and pass them into a Matplotlib object. So let's introduce you to this package here. Matplotlib is sort of the original visualization library for Python. There are other packages that are built on top of Matplotlib and made a lot of cool stuff that extend above and beyond, like Seaborn and the others are leaving me, but we'll go through some of them later here. For now, let's keep the data we've already used. I've already got a data frame here with the insurance charges data, and I want to simply create a plt.scatter object, and I'm going to pass into that a set of x coordinates and y coordinates, a set of two arrays, and each array represents the column. So let's do data frame dot, and I always forget which one, if it's the x or the y first. I think it's the x, so let's say age here, df dot charges here. And let's start by just printing that out. Okay, perfect. So it gives us this matplot collections, gives us the a data type here of the output. But here we see something very interesting about this data. Remember when we looked at the correlation coefficient, it was 0.299 with a very significant p-value, which means there's a strong relationship between them. And you can see here in the trend, there's definitely a strong trend to this data. But very interesting that we've got three unique groups clearly. One where it's very tight together, another here where it's a little bit more spread out, but then even another up here where it's also spread out. So most dots are here, second most here, maybe a slightly fewer here. Okay, well that's useful. Let's make this chart a little more useful, and let's give it a title. Oops, title. There we go. And let's pass into that just the text of the title we want, like insurance age versus charges or something like that. All right, perfect. Now we've got ourselves a nice title right up here. See how now it's giving us the data type of the last thing that we put in? One way we can get rid of that is use the plot.show method. So show clears the object from memory and displays it at the same time without that data type message at the top. So I always save this for last, since I know it's also going to clear the chart from memory. So anything else I want to add in here, like plot.x label age and plot.y label charges need to come before that plot.show. All right, so now I've got my x label, y label, my title. This is looking pretty good. All right, what should we do next? Well, let's add a little more to this chart. So I'm going to take you back to the book so you can follow along and see what I'm going through here. So bivariate num viz. We just finished the 16.1. Now in this chapter you'll see I use some different data sets too. We've gone through the exact same concepts here. What I want to do next though is let's split it here into two groups. This is a great example. So let's split between smokers and non-smokers. So we've got that chart. I'm going to copy this so I can create another one down here. And I want to create two data sets and put both of them on the same chart. So what I'll do first is let's make a df smoker and df non-smoker. And I'm going to set this one equal to df, and we're going to filter out of this df smoker equals yes, and we only need out of that, no, we need all of it, so I'll keep that. I'll copy all this, and this is where smoker equals no. So I've essentially divided the data set up into two halves. If you're not sure what those are, let me show you what we're dealing with here. Let me print one of them out. df smoker. Oh, seriously. Even after doing this for a while, you get old, you still make dumb mistakes. There we go. So all smoker is the same fields, but for only those who are smokers, right? I've just simply filtered out the no's from this data set. So now that you understand that, and you get that non-smokers are the same thing, what I want to do here is let's create two scatter plots and put them on the same plot. So rather than df age and charges, I'm going to have df smoker.age and df smoker.charges. Whoops. Enter. And now let's add non. Awesome. Now what it's done is it's used this categorical feature, smoker versus non-smoker, which I get at with different data frames, to show me the difference here. And now I can start to clearly see, it's one of those two. I'm guessing it's the non-smokers who consistently cost far less, and it's the smokers who cost a lot more, and then I've got a mix of the two here in the middle. So there's something else that causes people to cost right around this amount. All right, that's kind of cool. It'd be nice if we had a legend though, right? No problem. plt.legend. But we're going to need to do one more thing before this will actually give us a legend. So notice when I do that, I get this little message, no handles with labels found to put in legend. What does that mean? Well, it wants one more parameter up here in each of these scatter plots. And I believe it's just label equals. We'll call this the smokers. Label equals non-smoker. Whoops. I don't know if that's supposed to be capital S or not. Who cares? All right. Beautiful. Smokers, non-smokers. And basically by default, it'll try and find the place on the chart automatically that has the fewest dots, so it's not overlapping as many. So for example, sometimes I'll have a scatter plot where most of the dots are up here on this side with a few out here, and it'll put it down here in the lower right corner or upper right or something like that. All right, well, not bad. We've got ourselves a cool looking chart. Let's do one more thing. Sometimes we may want to pull out some of the dots. For example, see how these are all overlapping so much down there? I'm going to reduce the sample size by, let's take this and I'm going to call this smoker reduced, and this one smoker reduced, non-smoker reduced. And I want to simply, I'm going to take the prior data frames that I already made, df.smoker, df underscore smoker. That's just the ones with just smokers, and say sample, and let's just get 50 plots out of that. 50 dots. So it's going to randomly select 50 of the cases. And down here the sample will run just the same way, except we want this to be non-smoker, and grab us the 50 matching cases for us to put in there. Oh, but what did I forget to do? Change this right here. I'm going to leave these errors in because I think often you'll do the same thing and it'll help you to see me fix them and catch them. So df smoker reduced, copy, paste, df non-smoker reduced, oops, reduced, copy, paste. All right, there we go. That's more like it. So we can see, all right, 50 here. So clearly it looks like we have about twice as many non-smokers who are at a consistent rate, and then up here we get, because remember there's 50 of each, and then up here we have two different rungs of, or two different tiers or levels of smokers. So there's something else causing smokers to have this division between them. So we'll drill down into that a little bit more later on. Next, let's do one more thing. We're having fun playing with Matplotlib here. This is just an aesthetic. I just want to show you how we can go through and change the markers for each of them, and the colors as well. So I'm just going to keep these same ones I was working with since I copied pasted, and we're going to use color here, and not percent colors, just color equals. Let's do a gold and maybe a color equals silver. So I'm going to show you that we can set our own colors. We can also set our own shapes called symbol. Marker. and we can pick any marker we want right here. Let me just show you the raised, the exponent, or whatever you want to call that, will give us a triangle, not maker, marker. All right, and for this one, let's do the letter O will give us a circle, and there's a list of these. You can just go to Matplotlib's documentation and get a full list of what character represents each marker type and all that kind of thing. All right, cool. Not bad. Let's now shift and learn how to make these plots even better. And I'm going to go back to this version right here. No, I think we better go with the original. I'm going to copy this one down. I don't need to re-import Matplotlib, so I'm going to drop that back out. But what I do want to do is show you how to add a regression line to your plot, which is extremely useful. So a line of regression represents a line that will minimize the sum of squared residuals between each dot and the line itself. What does that do for us? Well, a regression line is basically a bivariate prediction, meaning wherever that line goes, it's going to represent the actual trend of these dots. And so we can take any actual value of age for a new customer who walks into our store, and let's say they're 45, and then we follow that up till we meet the line, and that's what we were going to predict. They'll cost in insurance charges, $18,500 or something like that. So it's the beginning of a prediction that we'll get into more detail later when we do modeling. However, for now, it helps us simply understand the relationship between age and charges better. So we need to start by calculating this line, which we do by getting our good old y equals mx plus b formula from back in high school algebra. So we're going to import SciPy from SciPy. There's so many packages. Import stats. All right, and stats is a sub package in SciPy that gives us a variety of functions that are super useful. And just so you can see where we're at in the book, we're now into 16.2. I'm going to scroll us down. We're right about here. So I'm going to show you a technique that's kind of cool. First of all, let's just simply print out of here. We're going to use stats dot len regress. There we go. And we're going to pass into that our two arrays, age and df.charges. All right, so here's what we get. This len regress result. Slope 257, intercept, R, P, and standard error. Each of these should be familiar to you by now, except for maybe the standard error. Slope in the y equals mx plus b formula is our m, right? So y equals mx plus b. In these results, we're getting a y. Our predicted value is going to equal slope times x plus intercept. That's our b right here. So 315. R, that's just our correlation. We're already familiar with that. We learned how to calculate that a little earlier on right here in other packages. So the next two, p-value, you learned that one as well when we switched over to the, and now I've forgotten, also the SciPy package. I forgot, I've already imported it. I don't need to import it again. This last one represents the spread of the dots around the line. How spread out are they? So that's the error. How far off are we going to be in general on each of our predictions? So to save us having to, and I think I showed you this earlier, to save us having to store each of these in their own individual variable, what we can do is say, okay, now that we know what order they're showing up in, let's say that slope m, comma intercept b, comma r, comma p, comma error. And that will automatically store each of those numbers into those variables with those names, which is pretty useful. So that means what we can do next is use each of those variables one at a time to create another type of plot. So in this case, instead of doing a scatter plot, we're going to do a line plot, which is just plot, and we need to pass into it a set of x's and a set of y's, just like we did right here. So the x's are the actual values, and in this case our actual values are simply going to be the x-axis. So this goes from about 10 to 70 or so. So let's do that. Let's take a range object. Let's set x equal to range 10 to, what does it go to, 65? Let's try 65. Then y, what's that going to be? Well, okay, we need, and so each of these dots, we've got one dot at each one of these points along here. What I need is a dot that adds in the y-intercept first of all, which is, what is that again, 3100. So the y-intercept starts about right here, and then I need to go up by the slope value for each individual value of x. Every time I go out one on x, I need to go up 257.72. That's actually pretty straightforward to do. So here's how we're going to do it. Come here and simply go m, that's our slope, times x, which we just created right here in this range from 10 to 65. So it's going to take 10 multiplied by m, which was 365 or 274 or something like that, and then add on to it b, the y-intercept. So let me show you how the plot looks first of all. So here's our line. Oh, and you know, I should have even started at 10. My dots start here about 17. So I'm going to change this to about 17 as well. Maybe 18. It looks like it goes a little bit past 65. Maybe 18 to 66. How can we automate that a bit? Well, here's one way to do this. Come here, and instead of putting in 66, let's just grab df.age.max. And that'll return the maximum value of age, and input that instead. Although now I'm surprised, it looks like it's not even going quite to the end. Let's do this, let's find out. I'm going to print df.age.max just to see what that is. 64, huh. I'm not sure why it's got that difference there, but I'm not going to worry about it too much. All right, age max starting at 18, that looks good. We've got our line. Why don't we make this line a different color? That might be, nope, don't tab there, color equals, let's just make it black. There we go. Boy, that really bothers me that goes out there a bit. I'm just going to add my OCD here. I'm going to add 2 just to send it out. Well, whatever. Okay, I give up. So we've got our regression line. What's interesting is how far down it is. We have all these dots up here, and then these dots are only barely below the line. Well, why is that the line that represents the least sum of squared residuals? That's because there are so many dots here that are overlapping each other, and we just can't see them all. So the large number of dots here are pulling the line down closer to it. So this is a great way to understand the linear trend of the relationship between two variables. Because this line goes up, that tells us as people get older, they cost more in insurance charges. Doesn't go up a whole lot, it's not super steep, but also by plotting, we get this understanding of these 3 tiers of charges that we would have had if we just looked at the correlation. Well, the best thing is when we combine those stats together with these charts. So let's do that next. Let's combine text with some chart, our stats with our charts. But before that, I think I want to show you one more statistic that I want to include along with these other stats. And that's called heteroscedasticity. That's a fun word to say. It'll make you sound smart at parties. So heteroscedasticity represents the spread of dots around, across all values of x. So in this case, the spread is fairly consistent across all values of x, but that's just eyeballing it. We don't know if it is for sure. So we're going to calculate some stats to tell us that. So to do that, we're going to pull in a couple more packages. From stats models.stats.diagnostic, import het underscore Baruch pagan, and then I'm just going to copy that line and import het white. As you can see there's several measures of heteroscedasticity. These are probably the two most common, the Bruce-Pagan test and White's test. And they each have different strengths and weaknesses, so we just calculate multiple tests to get an overall idea of whether or not we have a heteroscedasticity problem. So hetero meaning it's different, scedasticity referring to the spread. So an assumption of this type of analysis is that the spread is consistent overall values. Why is that important? Well, if the spread was close together up here, then that means, again, we talked about this earlier, it means that our predictions would be more accurate here, and if the spread was larger on this side, they'd be less accurate over here. It just means that we can't trust that our predictions will be as accurate depending on what value of inputs that we're using. Anyway, let's go ahead and calculate a number for this. We've already got the data in here. I'm going to create what's called a model object, OLS, stands for ordinary least squares, and you'll learn more about this later on in the course, but for now, just copy this notation and we'll learn more about the details later. So OLS formula equals, and it's going to want the Y charges first, and then it wants this little tilde, and then the X value next, age. Now I've got to use the exact case sensitivity that those names appear in the data frame. Where is it getting the data from? That's just a text string. Well, that's what I have to pass in here, data equals df. So that's where it gets the data frame, and we're passing in all features, but this is how it knows which features to compare, right? All right, last thing here, once we've set this formula up, we actually need to call the .fit method, and what it's going to do, this line right here, is it's going to create this regression line and also go through, as part of that regression formula, which we've already done that up here before, but this adds a few other things we didn't get before, including it calculates the residuals for us, which is the difference between each dot and the predicted line itself. Well, this calculates it as well. However, this calculates it and stores it and makes it available for us to use, which we're going to need for these two tests right here. And I'm just realizing now that in order to use that OLS object, I'm going to have to say from statsmodels.formula.api import OLS. That's where we'll get that one from. Let's make sure that works. Beautiful. I've also flipped around age and charges. It actually doesn't matter which order these are in. If it's a bivariate heteroscedasticity test, which these are, it doesn't matter whether it's the X or the Y first. Anyway, now let's go ahead and calculate these tests. I'm going to call this one white test equals het white, and we're going to pass in model, this object we just created and fit right here, dot resid, and then that's the residuals, but we've also got to pass in the individual X values themselves. So we'll get that from model dot, it has its own model object dot exog. So it's actually model means look at this right here. Dot exog means grab the independent variable, the exogenous variable, well, that's all we need on that one. So I'm going to copy that line, and we'll change this to the Bruce-Pagan test, and then we'll call het Bruce-Pagan. All right, let's run that, make sure it works. Beautiful. Okay, they're stored. Let's just print them out in an output data frame. So I'm going to say output df equals pd.dataframe, and let's give it a few columns here. These tests are both going to return 4 values. It's going to return what's called a Lagrange multiplier statistic. I'm not going to go into the details behind how it works or what it means. If you want to learn more, a good regression class from a stats department will teach you this at our university. That's like stats 330, I think, something like that. Anyway, LM stat, LM p-value, you'll get a p-value whether they'll indicate how likely you are to not see this stat again, or in other words, the reverse of how much you can trust that this stat is going to be representative of future data collections. Then we're going to get an f-stat, which is a measure that it's also a good, it's based on the LM stat, but lets us know the effect size, and that f also has a p-value. Okay, let's add a couple rows now to our output df.loc. What should we use as a row index? Let's just use the name of the test. How about white test equals, we need 4 values in a list. Well, thankfully, that's exactly, we created those 4 columns because that's exactly what the whites test gives us, is a list with 4 values in it, in that order. So, I'll copy that, come down here, Bruce Pagan, dash Pagan. It's not one name. These are just the names of the statisticians who came up with these statistics in the first place. Output df, let's print it out. Here's what we got. Okay, LM stat, extremely small. The p-value, extremely large. And we get 4 different scores. In this case, all 4 of them have an extremely small f and extremely large p, indicating that the differences between the residuals across all values of x is fairly consistent. Now take a look here if we flip charges and age. I think I may have said earlier that it doesn't matter what order these are in, and often it doesn't, but in this case it very much does. I want to correct that, because look what's happened. All of a sudden this p-value is super tiny, and the LM and Lagrange and the f-stat are very large. So imagine just flipping this scatter plot around. You can see that the spread of dots going from the y-axis across all values of y is not consistent. So the spread here is very different from the spread here, and the spread right here is very different from the spread down here. And so having the y first in this formula is actually quite important. Although in some other cases it's often not. But we'll get to that in another chapter. For now, here's our nice little table. Overall, sometimes these numbers will be close to significant, and sometimes, like my whites test, will both have significant p-values, but my Bruce Pagan won't, or vice versa. Generally speaking, if they're all significant or all not significant, then I would conclude that, in this case, that I don't have problems with heteroscedasticity. Or if they were all significant, I would conclude that they are. If they're 2 and 2, then you could say, I'm borderline. If there's 3 that are significant and 1 that's not, you could say it's probably got a heteroscedasticity problem. Or the reverse, you could say it probably doesn't if 3 are not significant and 1 is. Anyway, so this is an important test to understand if we can rely on our predictions across all values of x similarly. And in this case, we can. However, even this heteroscedasticity measure is not really revealing this issue. The spread is the same across all values of x, but we still got this problem where we have 3 different tiers of charges. So we're going to have to keep exploring that a little bit. For now, before I get to that point, I want to show you a few more cool charts that you can use to visualize scatter plots that can be quite useful. So to do this, I want to start by importing Seaborn as SNS. This is a package that builds off of Matplotlib to make much nicer looking and some often more useful charts. So let's do this. Let's start by, I like to set my SNS.set colors, codes equal to true, which means it's going to allow me to use some color codes later. That will look really nice. We'll come back to that one. Next, I want to use or create what's called a joint plot. A joint plot is a base type of a plot that allows you to create a lot of variants of the same type of plot. So in the Seaborn library, you'll have like a base plot type that can then be further customized, and it'll have additional objects that are named for each of those customizations as well. Let me show you what I mean. All right, joint plot, first of all, it needs, I'm going to show you a different way to add in the data. I could just add in the list like I did before, but Python also uses named inputs. So I can say x equals age, y equals charges, and I'm just showing that you can have double quotes or single quotes, and then you can import the data entirely separately if you want. But I could also have just done df.age, df.charges, and it would have been fine. So let's run that, and here's our scatter plot. Why is it called a joint plot? You can see now. It's because it joins a scatter plot along with a histogram over here for each one of those variables. Very useful. So you could potentially skip the histogram back in the univariate stats phase because you know you'll get it right here. Once again, I've got this Seaborn. Because Seaborn's built on Matplotlib, I can do a couple of things. I can go ahead and do plt.show, and it'll clear it from memory and take care of that little message. Or another thing I can do is actually just put a semicolon at the end of that statement, and it does the same thing. Cool. All right, that's a joint plot. That's the base type of a joint plot. I'm going to copy this now and show you a few other types of joint plots. This is a joint plot where the kind equals, let's do the hex. I'll need quotes around that. Okay, how is this one useful? Well, what it does is it takes and creates a hexagonal shape to indicate how dense each of the dotted points are. So right here, because we have so many values on top of each other, it's really tough to see just how many dots are in there because it's actually not continuous data, it's discrete. Even though we have a lot of numbers, a lot of integers, it's not truly continuous, and so it's often easy for these dots to cover each other right here. Oh wait, no, I'm sorry, charges is continuous, I forgot it. Oh, no, I can't even remember. Oh well, either way, regardless, we have dots covering this up. And so this plot shows you, okay, it's not consistent across all of here. Most of your dots are down here. Young people who are not costing anything. And you don't see that with this version of it because they're all covering each other up down here. So hex plot, which is another name for this, is a great way to see exactly how dense the data is in various spots. Now, one more thing I want to show you is how to get rid of, now that we're not using this grid layout, we're not using these individual dots, we might want to just get rid of this grid that's back behind here. So I want to show you the seaborn.setStyle method. Right here, setStyle white grid. We've got a few options: dark grid, dark, white, ticks. So dark is, I think that might be our default. White grid's the inverse. Dark is the same color but without the grids. White's white without grids. And then ticks, I believe, is just the grids. So I think I want to do white. So I'm going to copy this. Come back here. White. And it's not just set style. I need to do sns.setStyle. There we go. So now my whole background's white, including around my histograms as well. I think that looks a little bit nicer, but this is something that is totally up to you. You can also go through and remove these grid lines off of these histograms if you'd like. That might be another good idea, but I'm going to leave that off for now. It's so easy to find stuff online, though. Just search for Seaborn, how do I remove grids from joint plot, or something like that. Anyway, I'm going to keep going. And next, I want to show you another kind of plot. Is also super useful. This one is going to be called a Kde plot. And notice I won't have to set the grid to be white again since it's been done up here already. Anyway, Kde stands for kernel density estimation. It's just basically a way of finding a smoothed line that indicates the flow of these binned values. And not only does it do that for the histogram, but here for our scatter plot as well. So it shows you more density. It's kind of like a topographical map. More density in these spots, and this one kind of helps indicate that there's both a bump here and a bump over there. I guess it's kind of counting these three dark spots all together. Kind of useful. This is a great way to visualize the more gradual changes where those are than the harsher cutoffs here of the hex bin plot. One more step further, let's use what's called a well, you know, before I go too much further, let me do a 2D kernel density plot. I'm going to say f.ax or comma ax equals, and I'm going to make a Matplotlib object so I can create what's called two subplots. plt.subplot and or subplots, and I'm going to set the figure size. I just want you to see how you can do this. You can change the chart to be bigger or smaller. Fig size equals, and this is width and height. I'll make it 8,6. Next, I'm going to say CMap equals sns.cube helix palette, and this is going to, let me say, as map equals true, dark equals 0, light equals 1, reverse equals true. I'll show you what all these mean in just a moment. sns.kde plot this time, and kde plot is built off of that joint plot object, but we're going to pass in df.age, df.charges, and then CMap. This is basically a set of attributes that I defined up here. CMap equals, and I created this palette of colors, and I'll show you what those mean in just one more second here. So I'm passing in that CMap object I just created. I'm going to say number of levels, let's see, equals, and let's set this to something like 60, so it'll be really smooth, and shade equals true. All right, let me show you what this is doing. Oh, you know what? I better set my background to black or dark. That would have been smart. Or, you know what? Instead of reverse equals true, let's set reverse equal to false. That's better. So what it's doing now is the same thing as it was up here, but I've got 60 levels instead of these handful of levels, and I set dark to be the dense area, and light to be the other area, the less dense area, and it comes up with this more gradual shaded indication of how dense the data is in various places. So sometimes it's a lot easier to interpret, I think, than these grid lines that simply get stacked closer together. But once again, I want to get rid of all that text, so I'm going to add the semicolon. It doesn't get rid of this future warning, though. This is just letting us know that, okay, pass the following variable as keyword arg_y. From this version, the only positional argument will be data. Let's not worry about this now. When this package gets updated in the future, then we'll modify the code. But you'll get these often in Python. It'll say, guess what, we're going to be changing things down the road. But not changed yet in this version I'm using. Okay, let's go on. This time, let's make a joint plot. I'm going to copy and paste some code into here from the book, so you don't have to sit here and watch me type it in case you want to copy paste too. So this is going to be x equals age, defense equals charges, data equals df, kind kde, yep, scatter, yep, all that looks good. Let's create this one. This is a way, let's see here, not a lot different. It's just another way of creating the same plot up here, but adjusting some of the parameters. Anyway, I'm not going to spend a whole lot of time on that one. What I do want to show you instead, though, is this very useful one down here. It's kind of a pain to make a plot for every single possible numeric to numeric relationship. And so the pair plot just is going to go through and create all of them for us. It's going to ignore the categorical features and say, all right, let's give you the default standard plot for each of these types. So drop NA simply gets rid of any null values, which we didn't have any in this data set, but that's okay. I guess I didn't need to have that this time. But .pair plot, yeah, automatically creates the scatter plots. And then along the diagonal, it creates, I don't know if you noticed, but histograms. So you wouldn't plot age against itself. That makes no sense. But instead, the histogram is useful. So histograms along the diagonal, scatter plots on either side. Now, why do these scatter plots look this way? Well, that's because children is a discrete variable. You can't have 1.5 kids. You can only have one. So all the dots fall right along the integer. So discrete data is kind of tough to visualize. You can, and a scatter plot is still appropriate, but you really have to have a line of regression when it's discrete data to let you see where the trend is, because all these dots are covering each other up. Anyway, I guess I'll show you one more. You can customize this pair plot. if I don't want to have the default scatter plot, I can go ahead and like adjust it to like a KDE plot instead. These take a long time, especially when you up it to something like 60 levels to try and get more continuous data. I'm going to pause the video while it finishes. Okay, here you go. Because I made 60 levels, it's too much. See how it's too dense? It's too hard to see where that is. So I think I'd back this off to something like 10 levels. Maybe that won't take quite as long to generate either. There we go. That's a little bit easier to see what's going on. All right, kind of cool. Let's move on though, and let's go back to this problem of having these 3 levels of charges that we didn't fully understand. One way to understand it in greater detail is with 3D plots. So I'm going to move on to chapter 16.5, or in your book, it's just the 5th section of whatever chapter you're on to analyze numeric to numeric visualizations. So let's first start with, I'm just going to copy paste some data here out of the book. Let's start with a 2D version of a 3D plot. So I'm going to stick with our insurance data here though, and we're going to be using a few libraries. We've already got these two, so I'll delete those. And I'm going to stick here with Matplotlib, but instead I'm going to pull in df.age, and this is our y technically. So, but I'll make this something like BMI, and then I'll put our y here, charges. I'm going to leave off our labels and title for now, but those are pretty straightforward. Oh, Matplotlib right here, so I'm going to change that to PLT. All right. Actually, in this case, I think it would have made a lot more sense to keep those labels on here, but we can tell what they are by the scale. So here's charges, here's likely BMI, and then on here is age. But see how it's at an angle now? I've split it up now by BMI, but it's just, this doesn't do me a lot of good. It looks even worse. So I just wanted you to see that this is possible. I can adjust Matplotlib to show me different angles of this plot, but much more useful would be creating a more interactive 3D plot. So that's where the Plotly package comes in. Plotly is also built on Matplotlib. However, as soon as I run a Plotly figure, I can't run a Matplotlib figure again because it's going to make this worksheet. It's going to add some metadata to it so that it can create interactive visualizations. So I'm going to pass in the data, and I'm going to use this format instead, X, Y, Z. Let me show you what we get. Oh, sorry, not data, DF. All right. Notice I can now move this around and get a better view of all 3 dimensions. Okay. So I can still see this age to charges issue there. How does BMI help? Well, let me rotate it until I get the BMI axis. So notice that when I flip it across the BMI axis, I have a similar relationship to charges as I do with age. What that means here is that the dots up on this end of this middle section, so my middle section is still probably smoker down here, non-smoker up here, and I have this middle section that's both smokers and non-smokers, but I can see that BMI is playing a role of spreading each of these out. Within each level, here, this is not really affecting charges a whole lot, BMI. The charges stays the same at all levels of BMI. However, right here, there's a bit of a trend that goes, it's sloped just slightly. As BMI goes up, I can see that charges also goes up slightly. Same here with those who are smokers, there's a continued effect of BMI right there. So see how there's our view of age and charges that we're familiar with, although I'd have to rotate it around to get it to look just like it did before. But anyway, this view shows me the BMI against charges view. Now that's useful. Let's modify this a bit and make this 3D chart a 4D chart. Let's say color equals We'll put in smoker. Okay, now we're getting somewhere. So back to our, let's do our age to charges view. I'm upside down, but that's okay. It takes some getting used to for sure. Right about there. All right. So charges here, they're all going up by age, but I can see my smokers are these with the highest charges, non-smokers the lowest, and they're mixed up here in the middle. If I rotate it to where I can see BMI, this now explains what's going on here in the middle section that has both smokers and non-smokers. I can see that those with the higher BMI, so there's two ways of getting to this middle group. You can either be a non-smoker with a high BMI or a smoker with a low BMI. But being a non-smoker with a high BMI pushes you to the highest level of charges. This is a great data set to illustrate the usefulness of 3D and 4D charts. But it doesn't even stop there. Now that we understand what's going on with this section right here, let's take it a step further and let's include something like, I don't know, let's do sex in there, and let's use that to create different symbols. So sex equals, oh sorry, I got backwards here. Symbol equals sex. All right. Now we can see that females are circles, males are diamonds. Does that add much? Do we see, are there trends where there's more circles or fewer diamonds or something like that? No, it looks like they're fairly spread out in both groups. It's tough to see when they're all overlapping, so let's zoom in. I'm just using the scroll button on my mouse. I might need to increase my plot area to see it though, but basically my circles and squares don't seem to have a trend. They seem to be fairly randomly spread out. So I'm going to conclude that there's not really an effective gender. But now let's turn our 5D chart into a 6D chart using something like size. So size equals, and one of our last variables is children. So size likes a continuous variable instead of a categorical variable. And so here you can see the size of the symbol is larger or smaller depending on how many kids they have. And once again, I see large and small that appear to be randomly scattered throughout. I don't see a clear trend of whether it's all large or all small. So based on this, I'm going to conclude that sex and children have little effect. By far the largest effect is smoker. Age clearly has an effect because there's a visual trend. As I visualize age against charges, I can see it goes up. And BMI also has this interaction effect, or it also has its own effect because you can see that as BMI goes up, charges, at least at this middle level, this is why it's an interaction effect, is at the bottom level, BMI plays no role whatsoever. Charges does not increase based on BMI alone. But right here in this middle level, and this is why BMI alone also doesn't explain it, but there is a slight trend to that middle group and to this group up here. So if you're a smoker, BMI is worse than if you're a non-smoker. But there's something else that's causing this group of reds right here, these people with high BMI who cost a middle amount, that's different from most people where BMI doesn't make a difference at all. So, very useful. This is why we do 3D plotting. This is the end of our bivariate to bivariate analysis. Hope that it all makes sense. Reach out to your TA's instructor with questions, and we'll move on next to categorical to numeric analyses.